Chapter 13, Topic 13.6, Specific Immunity and Vaccination. For this topic, I want you to be able to list and define the 4 different descriptors of specific immune states, discuss the qualities of an effective vaccine, name 2 major categories of vaccines and then the subcategories under each, discuss the pros and cons of killed or inactivated versus attenuated viruses, and describe the principle behind DNA vaccines. So in this overview, we're going to cover a short history of vaccination. We're going to talk about the 4 types of acquired immunity, types of vaccines, development of new vaccines, route of administration and side effects, and to vaccinate, who and when. I cover history more than I used to because I think it helps with the current trend away from vaccination. The first disease to have a vaccine was smallpox, so let's cover that first. Back in the bad old days, you had a 50% chance of surviving smallpox. If you survived, you didn't get it again, but you may have disfiguring facial scars. That's where the term poxmarked came from if you read historical fictions. But because you never got smallpox again, unlike influenza or foodborne illnesses, people thought, well, may as well get it over with, and they would snort pus or ground up smallpox scabs to intentionally get the disease. Then they noticed the death rate was closer to 1%. Well, that's better odds. The process of snorting ground up scabs is called variolation. It was probably a better way to contact the virus because there are smaller amounts of virus in dried scabs than in juicy sneezes, which gives your immune system time to get going. Anyway, variolation was popular for a very long time. Then in the 1600s, Dr. Edward Jenner in England noticed that milkmaids that had contracted cowpox from their bovine charges didn't get smallpox when it came through. Cowpox is a very mild disease. So Jenner thought that might be a better way of preventing smallpox deaths than variolation. I love how he started with a kid. That tells you how bad smallpox was, that this mother was willing to risk her kid with an unproven treatment. Anyway, this process, which became known as vaccination with vaccinia virus, has a mortality rate of less than 0.01%. That's a good thing. Unfortunately, it was another 200 or so years before Louis Pasteur developed another human vaccine, which was for rabies. The death rate for naturally acquired diseases is still a whole lot higher than deaths from vaccinations, by the way. So, vaccination is a type of active immunity because your body develops memory cells from the process. See, it's active. Natural active immunity comes from recovering from an illness. There are passive forms of immunity where you receive antibodies from somebody else that made them, so you don't make your own activated immune cells. Fetuses receive passive immunity from their mothers when IgG crosses the placenta. You can continue to receive passive immunity from your mother through IgA in breast milk. Artificial passive immunity is when you receive a gamma globulin shot or receive antibodies through an IV, like the woman in this photo. Artificial passive immunity is indicated for patients that are incapable of mounting their own immune response, or to give a patient time between exposure and when they would mount their own immune response. Think needle sticks when you know the needle is contaminated with a particular disease. So let's talk about types of vaccines. There are whole cell vaccines, where we're using the whole cell, and subunit vaccines, or we're using parts of organisms. A live cell can be weakened or attenuated so it doesn't do well against your immune system. You should mount an immune response to it without becoming ill. One tends to produce more memory cells from a live or attenuated vaccine because the pathogen replicated within your body. Killed cell or inactivated virus vaccines are composed of, well, killed bacteria or inactivated viruses. Obviously, the pathogen won't be able to replicate within your body. The killing/inactivation process may have changed the shape of some of the antigens so you don't have memory cells for the real thing, so to speak. But generally, we have processes for avoiding this, and you generally get a pretty good immune response from it. Some pathogens we can't grow in the lab, so we can't attenuate them or grow them for inactivated vaccines. For these pathogens, we use subunit vaccines. We snag the gene from the virus or the bacterium, and we grow it in something that is less fastidious. Remember back to the chapter on biotechnology and recombinant DNA. Another type of subunit vaccine is the toxoid vaccine, which is composed of inactivated toxins. The body produces antibodies against the toxoid. This is useful when the cause of the disease is from a toxin rather than from the replication of the pathogen. Think tetanus. There's generally a lower immune response to subunit vaccines because the body is presented with fewer antigens, but they get the job done, especially in the case of toxoid vaccines. You do need to have boosters for subunit vaccines more frequently than you do for whole cell vaccines. We don't have vaccines for all the diseases that are causing pain and suffering in the world, so we're constantly working on new vaccines. One of the new types of vaccines that looks promising is the DNA vaccine. We take the gene for the antigen that we're interested in and we put it in a plasmid. Rather than putting the plasmid in another microbe, they inject it into you. A few of your cells take up the plasmid and start producing the antigen on the surface of the cell. This leads to the same level of immune response as a live attenuated vaccine, at least in animal models. Vaccines have a number of different routes of administration. Most vaccines are injected. We have a few attenuated vaccines that can be administered through a nasal spray or orally. Both the spray and the oral administration are received better than a shot. But all is not rosy in the vaccine world. You've probably met someone who has become sick or has had a reaction to a vaccine. That someone may have even been you. Generally, the chance of a side effect is lower than the chance from having side effects from receiving the disease naturally. For example, panencephalitis is a side effect of the measles vaccine, where you have progressive neurological dysfunction, but you are 10 times more likely to contract panencephalitis from getting the measles disease than from getting the measles vaccine. But the risk is there. Live or attenuated vaccines can back mutate to the real or wild type pathogen. In other words, you get the disease from the vaccine. That was more of a problem with the polio vaccine than with other live or attenuated vaccines that I'm aware of. But it was still a real problem with the oral vaccine, and that's part of the reason why the oral vaccine for polio is not common in this country anymore. Killed or inactivated vaccines can be improperly processed so that you have a live vaccine or an extra crispy ineffective vaccine. You can always get another vaccination if it's extra crispy, but we always use the vaccine strain in inactivated or killed vaccines just in case it goes in the other direction. Vaccines can be contaminated with opportunistic pathogens if the injection site is improperly disinfected or if conditions in the factory aren't sterile. Now, this wasn't a vaccine, but we did have a serious case of contamination with steroid injections last year. It was a big problem. People were getting meningitis from being injected with contaminated steroids that basically gave them fungal meningitis that they wouldn't have gotten otherwise. Regulations for the conditions in factories that produce vaccines are very, very strict, but there's always that possibility. Some people have neurological side effects for no known reason. And, of course, there are some people who are allergic to parts or a part of the process of the vaccine, such as to the eggs that the influenza virus for the vaccines are grown in. All of these things need to be taken into consideration before receiving a vaccine. But, as I've said before, the risks of the vaccine are much less than the risks associated with the actual disease. So, who should we vaccinate? It is recommended that all children be vaccinated for childhood diseases. This protects the children from diseases that kill children in other parts of the world, like measles, whooping cough, and diphtheria. Other than boosters for vaccines like tetanus, most adults don't need vaccinations until they become older and their immune system decreases with age. Of course, if you are traveling to areas where the diseases are still prevalent, whether you're traveling for pleasure or in the military, you will be receiving the vaccines for diseases in those areas. And of course, healthcare workers receive vaccinations for diseases that are more common in healthcare facilities, such as hepatitis B and influenza. Yeah, that covers an awful lot of adults. Maybe we should have said all adults should be vaccinated. Anyway, that's it for this chapter. I hope you enjoyed it. And as a reminder of what I want you to remember from this topic, you should be able to list and define the 4 different descriptors of specific immune states, discuss the qualities of an effective vaccine, name the 2 major categories of vaccines, and then the subcategories under each, discuss the pros and cons of killed or inactivated versus attenuated vaccines, and describe the principle behind DNA vaccines.